this afternoon. Anyway, so Voronov is going to give us a mini-series on universal algebra.
Thank you. So I will be talking about graphs and formal algebraic quantization, also about trees and operas, and finally about graph homology. Just as it's supposed to be on, if you go to the website of this conference and click on the schedule of this conference, you'll see those topics. And actually, when I was commissioned to give this mini course, I was not only given the title, but also the list of topics to talk about. And I sort of took it literally. Okay, well, I took it literally as sort of God-given. That is coming from Dennis. And and so I'm going to follow it. But the rumor is that, in fact, it's not God-given, but rather it's given by the apostles, by the organizers of the conference. And so I could have sinned, if I had known then, that I could have sinned and then confessed. So, but I will take the righteous way and go on with the topics suggested by the organizers. So, first of all, well, today's topic is graphs and deformation quantization. And I want to talk first of all briefly about deformation, algebraic deformation theory. Which starts with the following problem. Suppose that, or maybe starts with the following definition. Suppose that A is an associative algebra. I will be talking about the deformation theory of associative algebras. So suppose that this is an associative algebra over a field K of characteristic 0. And then a formal deformation of it. Oh, characteristic K equals 0. Okay. And the formal deformation quantization, a formal deformation, no quantization yet. A formal deformation of A is a KT linear, actually bilinear, multiplication law on the formal power series, formal Taylor series with coefficients in the algebra A. So this formal multiplication law is denoted by MT of AB, which is equal to, it's a series in T, so it's equal to, let me start with 8 times B plus M1 of AB T plus M2 of AB T squared plus dot dot, a formal power series in T, where A and B are elements of the algebra A. So it's a formal multiplication law, which may be expanded this way. Well, every multiplication law may be expanded this way, of course, but the point is that it should start at the 0th order. In T, it should start with the original multiplication of the algebra. So A times B here is the original multiplication. And also it should satisfy the associativity condition. Huh?
the rest of A of T.
Um,
How's multiplication defined on the other elements of A of T?
oh, by K-T by linearity. Yeah, so this formula determines that, of course. And, well, satisfying the associativity condition that MT of MT ABC equals MT A MT BC. So this is what I will be talking about in today's lecture, and I will be in fact, the goal is deformation quantization, which will come later. But so far, let me assume that this definition is right. That is, this defines, well, in fact, this defines a new structure of algebra, of an associative algebra on the space A of T, and the sense that it's a deformation of the regional product is contained in this formula. So it is sort of what we expect from a formal deformation to be. And now I want to look at it from some kind of a quantum viewpoint and think of it and pass to the semi-classical limit. Quasi-classical limit. To the quasi-classical limit, thinking of T as a quantum parameter, like the Planck constant. Yes?
Is there any obvious way of saying that the result of such a multiplication is an element of the algebra again?
Yeah, that's a common point of confusion, in fact. I also, yeah, when you first see this, this formula, you're talking about this formula, then you're sort of puzzled in which way you should multiply. But actually, there is a unique way to understand each side of this equation. Now, let me think about T as quantum parameter, just for a second, such as the Planck constant, which in Peter van Nieuwenhuizen lecture was given as for mathematicians to be 1. So, and if I let T go to 0, then I can notice the following structure inherited by a deformation, by a formal deformation. Then A inherits, not only it inherits back the product, the original product, dot product A dot B, but also a bracket, a Poisson structure, Poisson algebra structure, with the original multiplication being, of course, M T of AB evaluated at T equals 0, and the Poisson bracket being 1/2. That's why I needed characteristic 0 there of M1 AB. Well, maybe I should first write the formula. That it will be the limit as delta, as T goes to 0 of MTAB minus MTBA over T. So this limit obviously exists, and moreover, well, maybe it's 1/2. Yeah, 1/2 of that. And moreover, it's equal to M1 1/2 M1AB minus M1BA. So this brings us to some kind of physical road with this named Poisson structure and so on. And backward, well, if so, taking this viewpoint, we can say that if we have a deformation quantization, then we have this Poisson structure as the classical limit of it. And the deformation quantization problem is the inverse problem with respect to this viewpoints. Namely, given a Poisson algebra, so deformation.
Are you assuming A is commutative?
I think he is for this discussion.
Oh, that's a good point. Right. It's a.
A is at the top of your first one. A is in
Yeah, that's right. I have to assume that A is commutative over here. A is, say, that's a good point. If A is commutative, then we have the statement. In the Poisson algebra axioms, you do have the axiom of commutativity. Oh, I thought I would write here. Oh, okay, sure. And actually, the proof of this statement is very neat and simple. The proof of the statement that you get a Poisson algebra as the limit with respect to those operations. You know, to check that you have a Poisson algebra, you have to check a few identities. That this product is a commutative associative product, that this guy defines the structure of a Lie algebra, and that there is a Leibniz rule, a distribution law between the two, that bracketed with an element is a derivation of the dot product. Now, to see this, that you get that all of these conditions are satisfied, a neat way to do it is to look at, to notice the following: that if you have a deformation, a formal deformation of A, then itself this algebra A of T is in a certain sense a non-commutative Poisson algebra with respect to the product MT of AB and the bracket, which is M, the commutator, in the sense of this. So maybe let me move this a little bit. Oh, I was not allowed to do that. Oh, to the center. Okay. So, in a certain obvious sense, you get a non-commutative Poisson algebra with respect to these operations on the very original space, and this inherits all the identities that you need to check that in the classical limit you get a Poisson algebra. Now, the definition of deformation quantization problem is that goes as follows. It was posed in this way by Bain, Flatto, Fronsdal, Lichnerich, Sternheimer. I think I put all the names, at least the initials, right. And it says that given a Poisson algebra A, construct a deformation, a formal deformation, first of all. So it is, well, maybe I'm talking about a formal deformation quantization problem. Of course, you may always talk about convergence issues. So a formal deformation of A such that M sub T of AB is given by A dot B, then in the 0-degree term by some M1T, M2, where M1 is related to the given Poisson bracket. So where M1, where M1 AB minus M1 BA, 1/2 of that equals the given Poisson bracket. And of course, it should be associative because it should be a deformation, a formal deformation. Now, a way to, oops, this one doesn't appear to be movable. Okay. maybe I just ran out of power. No, I think there was something put inside here. So, yeah, there is something deliberately stuck inside. And actually, I already broke this little thing that it was here. Okay. All right. Now, the main tool in studying deformation theory and deformation quantization problem, as was mentioned by Boris Tsigan today, is the Hochschild complex. So this is a complex of vector spaces denoted by this sign. And where CNAA is defined as HOM, the space of n linear maps from the nth tensor power of A to A, and the differential was, well, it's not really inspirational to write down this formula for the differential, as you probably guessed it from Boris' talk. And anyway, it was in Boris' talk in the morning, so the differential was defined as in Tsigan's talk. Now, the Hochschild cohomology is, of course, also defined in Tsigan's talk as the kernel of D over the image of D as usual, and then the main statement relevant to deformation theory is that this complex is actually a differential graded Lie algebra. And when we know that, we will be almost done with deformation theory, and I will be able to move on to deformation quantization. So far I'm purely in the subject of algebra and not quantizing anything, just deforming. The remarkable structure which is on the Hochschild complex is the Gerstenhaber bracket, which is a map. It's n from the tensor product of C of the mth component of the group of m cochains and the space of n cochains, tensor space of n cochains, to C m plus n minus 1 cochains, and this is called the G bracket. And again, it's not very inspirational to write down the expression for the bracket, except in the specific case which I am going to write down in a second. Well, but there is a conceptual definition of, actually Gerstenhaber gave this bracket just by presenting a formula, but there is a conceptual definition of it. When you, I belong to Jim Stashev, which goes as follows. You can identify the Hochschild complex with the space of derivations of the tensor coalgebra generated by A of 1, where A is the suspension of the space A, that is the shift in degree of the space A. So in general, if you have V a vector space, then V of k is defined as a graded vector space whose nth component equals the k plus nth component of the original space. So actually this puts everything, all A, since I didn't assume it was graded, in degree -1, and this suspension operation. And then I consider the tensor coalgebra, just the standard tensor, well, algebra but I'm looking at the coalgebra law, which is standard there. And I'm looking at the derivations of this coalgebra. People usually call those co-derivations, but actually they are derivations of the corresponding algebraic structure, so it's better to call them derivations. Well, the point is that this coalgebra is free as a coalgebra, and therefore every derivation on this coalgebra is determined by its projection onto this guy, onto the first component.
Over n on the left, right? Direct sum over n on the left. You're right.
Direct sum over n? Oh, yeah, that's true. Thank you. Thank you. So it's the sum over n. So the, well, as we know, for derivations of a free algebra, everything is determined on the component of degree 1. Here, everything is sort of co-determined on the co-component of degree 1, and that's why we have this statement. And so this is the Hochschild complex, which is represented like that, as a space and as derivations, and therefore you can take the bracket of those derivations. If you bracket two derivations, you will always get a derivation, and this is a way to define the Gerstenhaber bracket. Okay. Well, in fact, this shift in degree makes not the very Hochschild complex to be a Lie algebra, a graded Lie algebra, but the Hochschild complex shifted by 1. So with the statement is that this gives a graded Lie algebra structure on the Hochschild complex, which dot means that I'm summing up over all possible n's, shifted by 1, and also on the Hochschild cohomology, shifted by 1. And then the main statement, sort of the cornerstone of deformation theory, is the following simple proposition, that saying that a formal multiplication law m sub t of AB equals, which is expanded into the powers of the parameter t as m0 plus m1 abt plus so on, is so far not assuming any properties of this multiplication, like not assuming the associativity. So a formal multiplication like that is associative if and only if the Gerstenhaber bracket of MT with itself vanishes. And it's very easy to prove this statement. It's just one line. If you know this formula for the bracket, for the Gerstenhaber bracket, then, which I didn't show, didn't put on the blackboard, but I will put it for two Hochschild cochains, namely for the case n equals 2, which are all of these guys m0, m1, and so on. These are bilinear maps on A, and they are two Hochschild cochains, Hochschild 2 cochains. So on two cochains, the bracket, the proof of this is that on two.
Without saying it, extending operations to the formal power series without saying it, right? MT is in the formal power series.
Yes, it's in the. Yeah, it's. I'm talking about a formal multiplication law, and so it's associative as a formal multiplication. That is, it provides a deformation, a formal deformation of the algebra, if and only if MT equals 0.
What I'm question is, MT is
Oh, yeah, yeah.
Extended by the
Yeah, extended by T linearity. Yeah. Yeah, but you extend this bracket by T linearity on the bigger space, on the Hochschild complex of A of t. So the G bracket looks like this. Is MT of AB. So I'm computing MT of ABC. That is equal to MT, well, let me see. Actually, it's twice that. MT ABC minus M sub T A M sub T BC. So this statement, after you know this expression, is completely tautological. This is the associative law. And here we go. This is the Gerstenhaber bracket at the same time. So the vanishing of this is equivalent to having the associativity condition. On the other hand, this is really fundamental because what classical deformation theory has been doing, well, given that those blackboards are non-movable, am I allowed to use this? No. Okay, so usually classical deformation theory takes some kind of a perturbative approach to this, and one usually is interested in extending a deformation which is already done for the first few MIs, extending it a little bit further. And so the statement, and this is the main statement of deformation theory as it was done by Gerstenhaber, is that first of all, a formal multiplication MT of AB equal to A times B plus M1 AB T. So we already have a multiplication in the 0th degree, in the 0th order, and then we are interested in extending it further on. Then this multiplication is associative modulo t squared if and only if M1 d of M1 equals 0, where d is the Hochschild differential. So therefore M1, in this case, M1 defines a cohomology class, since it lies in the second. Since it's a two-core chain, it will define a two cohomology class in the Hochschild cohomology of A. Now, the second statement is, suppose that you already extended your deformation so that it's associative modulo t squared. So suppose a formal multiplication law as above is associative modulo t squared. Then it may be extended, well, yeah, then the existence, let me put it like this, the existence of M2 such that MT is associative modulo t cubed is equivalent to vanishing of the Gerstenhaber bracket M1 with itself in the homology. So in the Hochschild, in the Hochschild cohomology. Again, this statement is, again, tautological, although I guess it was quite a discovery in the old days that you can describe deformation quantization perturbatively using Hochschild cohomology. And the proof of this statement is really easy. You just compute you just write down, expand this equation in terms of powers of t. And expand this equation mt equals 0 in terms of powers of t. And then, so expand mt, the proof is expand in t, and then you get in t to the 0th, you get 1/2. Well, let me write it 1/2 of this. So it will be 1/2 of m naught equals 0. Then, which should be true if m naught, if AB was equal, if m naught was given by the original product, which was already associative. So in this case, it is true that this is satisfied. Now the next term looks like, terms by T1 look like dm1 equals 0. And so this proves this part. Now the next part, terms by T squared, collect as dm2 plus 1/2 m1 equals 0. And this gives you, and this is a restatement of part 2 of this corollary. So you can go on your own and construct a very nice perturbative deformation theory if you expand it further. But this is all you can do this way.
Is
Now,
the hypothesis dm1 equals 0 the same as saying m1 defines a Poisson bracket?
no.
Yes.
M1 equals M1 bracket M1.
M1 bracket M0 is 0.
dm1.
Is that hypothesis the same as saying m1 defines a Poisson bracket?
No, it just this is equivalent to the Leibniz rule.
Which is the
Yeah.
bracket rule.
Oh, sorry, because you need the other equation, the Jacobi identity, as well, coming from this.
Oh, yes.
Yeah. So you need two equations, and this is 1, this is 2. Okay. Now let me leave this topic alone. You can see what if you have this inverse problem, a problem of deformation quantization, and suppose that you are given M0, M1, which is the Poisson bracket, or such that the commutator of M1 is a Poisson bracket, then you would need to construct M2, M3 satisfying these equations, and this leads to an overdetermined system of equations, which is very hard to solve explicitly. So that's why I talked about this, just to tell you the idea of the story.
The Minicourse, I think we allowed to maybe debate a little bit. I mean, your proof over there that an associative algebra led to a Poisson algebra would work modulo t squared, wouldn't it? You get the
Yes.
Jacobi identity.
Yeah. Yeah, it will. Oh, modulo t squared. Well, but, you know, in order to check things modulo t squared, you have to be careful what it means to have modulo t squared. When you write down the fact that you have an associativity, you have to say it's modulo t cubed,
Oh.
right?
Oh, so
If you have terms up to t squared,
So if you have it out to t cubed, then
right?
you get Poisson.
Yes. If you have up to t cubed,
Okay.
right? Any other questions?
So how's the M equation that we look at?
Doesn't look as nice as that, but it's supposed to resemble the definition of an A infinity algebra. It is.
One thing I don't, returning to the Poisson bracket question, if I can, one thing I don't understand is the Poisson bracket is something you can check directly with M1, whereas the formulation of the second condition is that there exists an M2 such that. That seems strange, that existential statement should translate into just an identity in M1.
No, yeah, that's true. So I guess we want to let me see, that was M0, yeah.
But anyway, it has to be true, what you're saying.
Yeah, I know. That's why I'm puzzled.
You don't have to explain it. You can prove it.
Yeah, that was a philosophical question, and it got me stuck.
I mean, it's true. We just don't say it.
Well, just forget about this. Sorry. Okay. Well, I want to save time for deformation quantization because really cool things are on the way, and I want to finish with deformation quantization today to give me some freedom to talk about trees and operas tomorrow and the day after tomorrow. So here is the thing, deformation quantization. So usually it refers to a specific deformation quantization problem which is relevant to some geometric or physical setting. Namely, suppose you have a Poisson manifold. M is a Poisson manifold. Let me put the bracket as part of the structure. M and the bracket on it defines a Poisson manifold. And yes, and a little bit more that it's local, that is given by a bidifferential, biderivation. I mean, bidifferential operator of order 1. Huh?
You just say it's local.
Local. Yeah. But it's not just an algebraically given structure. It should be given by a local formula. By a local tensor. You see? Yeah, an example is a symplectic manifold, but there the structure is non-degenerate, and here it's, it's alpha. Let me put it. Jesus. Alpha ij, del I, del j, given, well, del if, del I g, so this is del j g. This is, so says that this is local, where this is a tensor, a 2 tensor, covariant or contravariant. I could never learn those things. So suppose we have a Poisson manifold, and then the theorem of which was the deformation quantization conjecture